A dam looks simple from a distance, a wall across a river. But in practice, it is a control system for gravity, water pressure, sediment, and time. Rivers naturally carry water downhill in pulses that change by season, by storm, and by decade. A dam interrupts that rhythm and turns fast, unpredictable flow into managed storage. That single shift is why dams became central to modern civilization. Instead of depending only on rainfall in a given week, communities can store wet season water and release it later for farms, homes, and industry. Instead of enduring every flood peak at full force, downstream channels can be moderated. Instead of letting elevation drop go unused, turbines can convert moving water into electricity. The same structure can serve all of these goals at once, but balancing them is difficult because each goal competes with the others. Holding more water improves drought security but can reduce flood buffer. Releasing water for power can conflict with irrigation timing. Flushing sediment can reduce short-term generation. So a dam is not just concrete or earth, it is a set of decisions about risk, reliability, and who gets water first when conditions tighten. Engineers classify dams into 4 basic structural families, and each exists because water pushes in predictable ways while terrain varies wildly. Gravity dams rely mainly on mass. Their own weight resists sliding and overturning from reservoir pressure, so they are usually thick concrete or masonry structures suited to strong foundations. Embankment dams are built from compacted earth and rock, often with zoned layers that control seepage and stability. They can span broad valleys and use locally available materials, which is one reason they are common worldwide. Buttress dams reduce concrete volume by using a sloped upstream face supported by a series of downstream triangular supports, transferring load efficiently while requiring complex construction quality. Arch dams use curvature to redirect pressure into the valley walls, making them material efficient in narrow, strong canyons but highly dependent on rock quality at the abutments. None is universally best. The type chosen reflects geology, river behavior, construction capacity, cost, and safety margins. Choosing the wrong type for local conditions can create hidden weaknesses that only appear years later under unusual stress, which is why classification is not academic labeling but the first major safety decision in the life of a dam. The dam story is older than modern engineering. One early example, the Jawa Dam in present-day Jordan around 3000 BCE, shows that even early societies understood storage as survival in dry climates. Later, the Hittite Empire built dams in what is now Turkey, proving that water control became a state-level capability tied to agriculture and political organization. By the 1st century CE, Roman builders advanced masonry gravity dam construction, expanding both scale and durability through systematic stonework and concrete-like materials. In medieval Europe, dams were not mainly about electric power, which did not exist yet, but about mechanical energy. Water wheels powered mills and mining operations, turning river flow into productive force. That long history matters because dam building began as practical craft, shaped by observation and trial, then gradually transformed into formal engineering. In the late 18th century and beyond, design methods shifted towards scientific analysis of loads, seepage, and materials. In the 20th century, reinforced concrete, earth-moving equipment, and industrial logistics enabled much larger projects across continents. So today's giant dams are not isolated inventions, they are the latest stage of a multimillennia progression from local water storage to national infrastructure strategy. If you strip away all technical detail, dams exist because societies need to move water from when and where it is abundant to when and where it is needed. Irrigation is the clearest example. A significant share of global food production depends on water stored in reservoirs and released during planting and growth cycles rather than during random storms. Without that buffering effect, yields become far more volatile and food systems less predictable. Urban water supply follows a similar logic. Cities need dependable intake through dry periods, not just during wet months. Industry depends on this reliability too, whether for process water, cooling, or sanitation networks. Hydropower adds another layer by converting stored potential energy into electricity that can be dispatched when demand rises. Flood management completes the core set of functions by reducing dangerous downstream peaks through time storage and release. Recreation, navigation support, and fish farming can also be incorporated, making dams multipurpose assets. But multipurpose does not mean frictionless. Every release plan favors one timeline over another, one downstream need over another. That is why reservoir operations are as important as structural design. A well-built dam with poor operating rules can still create serious social and ecological stress. Hydropower is often described as clean and renewable, and that description is directionally true because dams can generate large amounts of electricity without burning fuel during operation. Water stored at elevation contains potential energy. When released through penstocks and turbines, that energy becomes mechanical rotation, then electrical output through generators. The key advantage is controllability. Unlike some variable renewables, many hydropower stations can ramp output quickly, helping stabilize grids during demand spikes. In systems with growing wind and solar shares, this flexibility can become even more valuable. But hydropower from dams is not impact-free. Reservoir creation can inundate land, alter habitats, and change downstream temperature and sediment patterns. Generation priorities can also conflict with seasonal ecological flows. So the real policy question is not whether hydropower is perfect, but how to evaluate trade-offs against alternatives in specific basins. In some locations, dam hydropower delivers critical low-carbon reliability that is hard to replace quickly. In others, social and environmental costs can outweigh benefits. Mature planning frameworks treat hydropower as one tool in a broader energy and water portfolio, not as an automatic win or automatic harm. A dam is rarely just a wall and a lake. Most projects include integrated subsystems that keep operations safe and functional under changing conditions. Spillways are the most visible safety component. They release excess water when inflows rise, preventing reservoir overtopping, which is one of the fastest pathways to catastrophic failure in many dam types. Outlets provide controlled lower-level discharge, used for downstream flow support, drawdown, sediment management, and emergency operations. Sediment matters because rivers naturally carry particles that settle in reservoirs over time, reducing storage and affecting intake structures. Managed releases can help limit that accumulation, though every basin behaves differently. Where dams block navigable rivers, locks may be added so vessels can move between water levels, preserving transport corridors. Powerhouses, gates, sensors, and control rooms tie these elements together into a living infrastructure system. This complexity explains why long-term dam performance depends on maintenance and monitoring, not just original construction. Gates must operate when needed, instruments must detect seepage or deformation early, and operating teams must be trained for rare events. In short, reliability comes from systems engineering over decades, not from a single successful inauguration. Flood management is one of the most publicly visible benefits of dams, but it is often misunderstood. A dam cannot eliminate flooding everywhere, and it cannot always absorb extreme events without limits. What it can do, when designed and operated correctly, is reduce downstream peak discharge to safer levels. By temporarily storing part of a flood wave and releasing it later in a controlled pattern. That time-shifting effect can protect cities, farms, and transport networks. The challenge is that reservoir space is finite and conditions are uncertain. If operators keep reservoirs too full for water supply or power targets, less buffer remains for sudden storms. If they keep too much empty for hypothetical floods, water security and generation may suffer. Climate change intensifies this balancing problem by shifting rainfall patterns, increasing event variability, and making historical assumptions less reliable. Modern flood-oriented operation therefore relies on forecasting, adaptive rule curves, and coordination across multiple reservoirs when available. Even then, communication with downstream communities is crucial. Controlled releases can still raise river levels, and trust depends on transparent warnings and clear rationale. Effective flood management with dams is therefore as much about governance and data as it is about concrete. Because dams carry concentrated risk, failures become defining lessons for the entire field. When a dam fails, consequences can include rapid downstream flooding, infrastructure loss, and severe casualties. Engineers study such failures intensely to improve standards, but causes are rarely singular. Structural distress may begin with weak foundation conditions, poor abutment rock, or inadequate understanding of load paths. Hydraulic issues can arise from seepage through embankment zones, under-foundation piping, blocked spillway capacity, or uncontrolled overtopping. Geologic and seismic factors can trigger instability where assumptions about ground behavior were too optimistic. Operational errors also matter. Delayed gate actions, inaccurate inflow forecasting, or ignored instrumentation trends can convert manageable stress into crisis. The central lesson is that dam safety is layered. It starts with conservative design, continues with quality construction, and depends on lifetime surveillance, emergency planning, and institutional discipline. Redundancy is not waste, it is protection against uncertainty. Communities often judge dams by normal day performance, but safety performance is measured on abnormal days. The true test is how the system behaves when inflows exceed expectations, equipment misbehaves, or the ground moves. Preparing for those edge cases is the core of responsible dam stewardship. Beyond engineering, dams are political because rivers ignore borders while states do not. Upstream storage can alter downstream timing and quantity of flow, which directly affects agriculture, cities, and ecosystems in neighboring regions or countries. When water is scarce, population is rising, and climate variability is increasing, each new dam can be interpreted as either development necessity or strategic threat, depending on position in the basin. Disputes linked to dam building in countries such as Turkey, India, Ethiopia, and China illustrate this tension. Upstream governments emphasize sovereign development and energy security, while downstream stakeholders emphasize dependence, predictability, and historical use. The technical facts of reservoir operation become diplomatic issues because uncertainty itself has political cost. If downstream users cannot forecast releases, they face planning risk in farming, power scheduling, and municipal supply. Durable solutions usually require data sharing, notification protocols, seasonal coordination, and dispute mechanisms that survive leadership changes. In that sense, dam governance is a test of cooperative infrastructure politics. A physically successful dam can still be a regional failure if trust collapses. Conversely, transparent operating frameworks can transform a potentially divisive project into a shared stability asset, even when interests remain unequal. Public resistance to dam projects is not new, and its persistence reveals that water infrastructure decisions are social choices, not just technical upgrades. Organized opposition in the modern era, including protests as early as the 1870s against Britain's Thomere Dam, reflected concerns that still appear today: who benefits, who bears local costs, what landscapes are transformed, and how decisions are justified. Communities near proposed reservoirs may face displacement, livelihood disruption, or cultural loss. Downstream groups may worry about altered fisheries or changing seasonal flow rhythms. Environmental advocates may focus on biodiversity fragmentation and sediment interruption. Supporters, meanwhile, emphasize food security, power generation, flood mitigation, and long-term national development. These positions are often presented as absolute opposites, but in practice many conflicts revolve around process quality, whether impact assessment is credible, compensation is fair, alternatives were seriously considered, and operating commitments are enforceable. Good policy does not eliminate conflict, it makes trade-offs explicit and accountable. For viewers trying to understand dam debates, this is the key: arguments are rarely about water alone. They are about distribution of risk, distribution of benefit, and trust in institutions that claim to manage both. So what does the future of dams look like in a hotter, more volatile world? First, existing infrastructure will matter at least as much as new megaprojects. Many regions will focus on modernizing operations, improving spillway capacity, strengthening monitoring, and revising flood rules using updated climate data. Second, multipurpose coordination will become more demanding. Water supply reliability, agricultural demand, grid flexibility, ecological flow protection, and flood safety will need tighter integration, often across entire river basins rather than single projects. Third, political coordination will become a core engineering dependency. Without transparent data and predictable cross-border communication, technically sound dams can still produce chronic instability. Finally, public legitimacy will increasingly depend on whether projects can demonstrate long-term resilience and fair benefit sharing, not just short-term construction success. The dam of the future is therefore not defined only by height or storage volume. It is defined by adaptive management, the ability to keep delivering value under shifting hydrology, economic pressure, and social scrutiny. In that light, dams remain one of humanity's most powerful infrastructure tools, but also one of its most demanding tests of foresight, discipline, and cooperation. If you found this helpful, please like this video and subscribe for more explainers.